second question, question 8, is similar in the sense that we are tossing coins. So we are tossing a coin several times. And I want to know what is the expected number of tosses such that I get 3 heads in a row. So that can be given in different ways, because it can be that I start now. So now is times 0, and obviously I have not tossed my coin yet, and I start tossing, and I want to know what is the expected number of tosses such that I have 3h. Or I can also be in the situation in which now I already tossed the coin and I'm in front of a tail, okay? And I say, okay, from now on, I want to see what happens. So that was the first question. And the second question is essentially, what is the expected number of tosses in which instead of having head, 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 I have tails, heads, heads, okay? So I have THH instead of HHH. And again, my suggestion was to try to use Markov chains. I will find the unique solutions, mu1, mu_m, such that mu_j is equal to 0 if j is absorbing, and mu_j is equal to 1 plus the sum for k from 1 to capital M of pjk, these are the transition probability, mu_k if j is transient, okay? So solving this equation, I'm essentially able to solve, for example, the second exercise, exercise 8. So we keep on tossing the coin, which is fair. So the probability of heads and tails is always 1/2. And we are interested in knowing how many tosses on average, so the expected number of tosses that we need in order to have 3 heads in a row. And the second question, what is the expected number of tosses that we need in order to have tails, heads, heads? So THH, and in the first case, HHH. Now, let's try to think about what can be the state space. So we start from the first question. In the first question, we are interested in this. We want to know what is the expected number of tosses until we reach the situation HHH. When we start the game, okay, we can be in a situation, let me call it 0, okay, state 0, that can represent actually 2 possibilities. The first one is that it is time 0, okay? So it means that I have not yet tossed the coin, okay? So I'm starting really from scratch. I'm starting from scratch and that's it. But it can also be the situation in which I'm looking at my sequence and now I'm in the situation T. So I have tails. And from now on, I'm counting how many heads I have so that I have 3 heads in a row. Okay, so the starting point 0 represents both situations. Either I'm actually starting the game or I'm in a point of the game in which I'm in front of a tail, not of a head, because obviously that would be already the first H of the 3. T, conversely, does not belong to the triplet HHH. Okay, then if I have this state, what is the next state I can reach? The second state I can reach is state H. So I have 1H. From 1H, I can go back to 0 because I get a T, or I can go to the next state, which is HH. When I'm in HH, this is interesting because I don't go back to H, but I can go back to T because I have a new T appearing. And then we have what? H, H, H. Okay, so let's try to draw this chain. Remember that 0 represents either the beginning of the game or the situation in which I have a T. That obviously stops my triplet HHH. Okay, so if I'm in 0, what happens? If I am in 0, I can get an H, and if I get an H, I move to this state here with probability 1/2 because the coin is fair. But if I'm here, I can also extract a tail. So I can toss the coin and get tails. Okay, so what's the probability of tails? If the probability of heads is 1/2, the probability of tails is 1/2. So from 0, I can stay in 0 with probability 1/2. Notice the difference with what we had before. 0 is not absorbing, okay? So I can escape from 0. I can stay in 0 because if I have a T and I toss the coin and I get another T, I'm always at time 0. Or if I start the game at time 0 and I have nothing, neither H or T, and I toss and I get a T, I'm in 0 because T also represents that. So 0 represents everything which is not an H. If I'm in H, what can I do? I can toss the coin once again and I can get a double H with probability 1/2, or I can get a tail, and that means that I have to go back to 0. If I'm in HH, what happens? I can toss a coin and get an H, so this is even 1/2, but I can also get a tail, so I can have HHT. But if I get HHT, I'm no longer able to get a triplet of H. So it means that I'm jumping back to this 1/2. And then what do I have? If I am in HHH, the game is over, because this is what I'm interested in, is in getting 3 H's, okay? So the fact that I get 4, 5 is not important to me because I'm just interested in 3. So H, H, H is for me an absorbing state because my question is what is the expected number of tosses such that I get 3H, okay? So I'm not interested in 4, 5, 20, 1 million. I don't care. It's just this. So from 0, I stay in 0 with probability 1/2. I can jump to H with probability 1/2. From H, I can jump to double H, probability 1/2. From double H to triple H, in probability 1/2. If I'm triple H, I can stay there with probability 1 because it's the absorbing state. If I'm double H, I cannot jump back to H, but I will jump back to 0 because if I'm jumping back, it means that I got a tail. And if I got a tail, it means that I can no longer get HHH. I'm in HHT, so I'm resetting the game to 0. Okay, so this is my Markov chain. Again, if you want, you can represent this in terms of a matrix in which I have 4 states. So I have 0, H, 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 H. The same here, 0, H, 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 and let me write 3H here, okay? And then obviously the probability that if I'm in 0, I stay in 0, it's 1/2. The probability that I go to H, it's 1/2. I cannot jump immediately to double H, 0, 0. If you are in H, the probability that I jump back to 0, it's 1/2. The probability that I stay in H is 0, and the probability that I go to 2H is equal to 1/2, sorry, and 0. If I'm in double H, the probability that I go to 0 immediately is 1/2. The probability that I go back to H is 0, and the probability that I go to triple H is 1/2. And here is 1, 0, 0, 0. So this will be my transition matrix if I want to give the transition matrix representation. Okay? We start at time 0, so we start tossing from time 0, or we are in a situation in which the last state we got is a tail. Okay? In that situation, we always start from 0, and we want to know how many steps, and since every step corresponds to a toss of the coin, and how many tosses I will reach my my absorbing state. So what I have to do is to write the set of equations. Now, how many tosses I need in order to reach triple H if I'm in triple H? 0, okay? That's why we set mu H equal to 0. So for what concerns the other quantities, I just have to apply my equations, okay? So the equations that we have just considered. It is for mu 0, it is equal to 1 plus, remember it's 1 plus the sum for all the others. So the first one is just given from the formula. I could be more precise and show you how these formula are obtained, obviously, but this is not the goal of this course. Okay, so if I am in state 0, what happens? From state 0, if I look at my chain, I can stay in 0 with probability 1/2. Okay, so I have 1/2. This is quite annoying. Okay, I have 1/2 mu 0. Okay, plus 1/2 mu H, because I can go to this. The probability of HH associated to the state HH from 0 is 0. So if you want, you can also write that just initially to understand. But you see that obviously that those part disappears. So it's not relevant to us. Then what do I have? I have mu H. From mu H, I have 1 that is always there. So always remember that. And I have 1 over 2 mu 0 plus 0 mu H. Why 0? Because I know that I have to escape H. It's not there is no possibility that I stay in H, plus 1 over 2 mu H plus 0 mu H. Now, this term disappears, this term disappears. And finally, we have the last one. So we have mu H 1 plus the possibility that I jump to mu 0. So it's 1 over 2 mu 0 plus 1 over 2. If you look here, I have the possibility of jumping to H, okay? And the possibility of jumping to all the others are all 0, okay? So allow me to write this. Because the possibility that I jump to H is 0, the possibility that I stay in double H, it is equal to 0. Now, mu H is also equal to 0, so I can also delete this. Now, if you solve this, allow me to jump over this because otherwise it's taken too much time, but I can give you the solution. I have that mu 0 is equal to 14, mu H is equal to 12, mu double H is equal to 8, and mu triple H, we already know that, is equal to 0. So the quantity we are interested in is this. So we want to know what is the expected number of steps to reach 3H in our setting when we start from the beginning or when we start from a T. Okay, so we want to start from 0 and we want to reach that. That means that the expected number of steps that we need is 14. Okay, And how do you get this? By solving just this system here. Okay, so you just have to solve this system, and these are the solutions that you get. Now, the second question is similar, but we are no longer interested in HHH, but we want THH. But there is an important difference between the two questions, and it's the following. Now, also here, if you want, I can start from a state 0, which is the situation in which either I'm starting the game from scratch or I'm in front of an H. I want the first letter to be a T. So if now is an H, for me, it's state 0. The second situation is when I get a T. Then I have TH, and then I have THH. Okay, so this is my my state space. Now, what happens if I'm in 0 and I toss the coin and I get an H? This happens with probability 1/2. If I'm in 0 and I toss the coin and get a tail, then this is 1/2. Then what happens? If I'm in T, I can toss the coin and get H, and that this happens with probability 1/2. But there is also another situation which is interesting, and is I'm in T, and instead of TH, I get TT. But if I get TT, then what happens? This T can later be the T of TH or of another TT. And then also here, I will have TH and TT. And maybe this will be THH or THT. And then I have to start again. Okay, so I have all these possibilities. So if I'm in T and I toss a coin, it can be a tail, and I stay here with probability 1/2. Okay, because I want the T to be just the first letter. And then what happens? If I'm in TH, I can go to THH with probability 1/2. If I reach these, I stay here with probability 1 because this is my absorbing state. But if I'm in TH, I can also get another T because I can be TH, THH. That will be the stop of the game for me. But it can also be THT. So it means that I have to continue the game. So it means that from this, I can go back to this with probability 1/2. So you see that the chain is definitely different. Because in particular, there is this possibility that we are observing with respect to what we have seen before. So the states, in a sense, are still 4, they are not exactly the same, and the fact that I can have a T and the T can happen several times, I have this recurrence for what concerns the state T. So what happens now? I have to solve exactly the same type of equations as before. So I will set mu of THH equal to 0, because if I'm here, I don't need any single step to go to that state. And for all the others, I just have to solve the usual equation. So mu0, it will be equal to 1 plus 1/2 mu0 plus 1/2 mu t, okay? Then plus 0 mu th plus 0 mu thh, but I can avoid writing there because, I mean, it's obviously equal to 0. Then I have mu t, and mu t is equal 1 plus the possibility that I stay in mu t plus the possibility that I jump to mu th. And then I have mu th, and this is equal to 1, plus the possibility that I jump back to mu t, plus the possibility that I jump to mu thh. If you solve this system, I leave that to you. The solutions that I give you are mu0 equal to 8, mu t equal to 4, mu th equal to 2, and mu thh equal to 0. So what we are interested in is the expected number of tosses to get THH. So it means that we start from 0. And this is the expected number of tosses that we have. Okay?